Today, I have the privilege of introducing Professor DOROTA KORTE. She's a professor at the Laboratory for Environmental and Life Sciences, University of Nova Gorica, Slovenia. She holds PhD in physical science, specializing in electronics and telecommunications at the Faculty of Automatic Control, Electronics and Computer Science, Technical University of Slovenia in Poland. She also holds a master's degree in biomedical electronics from the same institution. She has played a pivotal role as a mentor for doctoral dissertations, guiding emerging scholars in their research endeavors. Her primary fields of focus encompass analytical chemistry, environmental chemistry, and physical chemistry. She is renowned for her work in developing and applying innovative analytical methods such as laser photothermal spectrometry (TLS), microscopy (TLM), and beam deflection spectroscopy (BDS). Professor Dorota's research extends into the realm of environmental chemistry, where she conducts precise measurements of metal concentrations in various environmental samples, including water and sediments. In the domain of physical chemistry, Professor Dorota delves into advanced materials in various forms, such as solids, thin films, and multi-layered structures. On behalf of all the RIOS members, I welcome you, Professor, to this webinar. Additionally, I also welcome all the invited guests and participants to the webinar. Distinguished participants, please permit me to respectfully invite Professor Dorota KORTE to begin her presentation. Professor, you have the floor.
Thank you very much for your nice introduction. Hello, everyone. It's very nice to meet you here. So, as it was said already introduction, I came from Laboratory for Environmental and Life Sciences at the University of Nova Gorica in Slovenia. Yeah, Slovenia is a very small country in the south part of Europe, and university is located exactly at the border with Italy. Although Slovenia is very small, its surface shape changes a lot on the very short distances from very high mountains on the north to seaside area on the south. So Slovenia is very attractive touristic destination, so you are welcome to visit us. So, as it was already said, I came from University of Nova Gorica, exactly Laboratory for Environmental and Life Sciences. Our main research areas focused on so-called laser-based analytics, develop different materials with the focus for environmental application, as well as cell biology research and biotechnology development. And my research area is related to the first point of all developed in our laboratory. The main interest is focused on the development of highly sensitive spectroscopic methods for determination of different compounds in environmental and biological samples as well. So, I mean, it can be different types of pollutants, pesticides, heavy metals, but also biological compounds as at the level of acetylcholinesterase in the blood as the indicator of degeneration diseases. So the very first technique that was developed in our laboratory, it was a so-called thermal lens spectrometry that is very often during the analysis coupled to different bioanalytical techniques as flow injection analysis or liquid chromatography. But since very often, especially the biological samples are of limited volume, thermal lens spectrometry was further developed to thermal lens microscopy, and the detection was moved to so-called lab-on-chip chemistry. So we were able to study different processes on microspace. So we drastically decreased the amount of required sample and decreased the same time, the time of the analysis. The last direction of research that we develop in our laboratory, this is the beam deflection spectrometry. So we use that technique to study thermal properties of different advanced materials, as well as all properties that influence the values of thermal properties. And about that last technique, the beam deflection spectrometry, I would like you to tell you during today's presentation. So what it is or how works the beam deflection spectrometry. This technique belongs to a group of spectroscopic techniques that measures the light absorption in order to quantitatively identify the substance of interest. So if we have a sample of our interest, we illuminate it with a modulation radiation that we further called it excitation radiation. And what happens to the samples? Of course, the sample absorbs the radiation from excitation radiation, and then later, during different non-radiative de-excitation processes, it turns it into heat. So what we received? We received the temperature oscillation in the sample and later also in the fluid above the samples. Yeah. So in the first step of the analysis, we need to find the shape of temperature oscillation induced in the fluid over the sample. So we need to solve the so-called heat diffusion equation with the boundary condition that are chosen as equality of temperature distribution and heat flow at all boundaries of our experimental structure. So I mean between the sample or all layered of the sample if it's multi-layered, and the adjusting fluid. Yeah. So solving that equation, we received the temperature oscillation, their amplitudes and phase. And these two parameters contain information about the sample properties in the first step about its thermal parameters. So I mean how the sample conduct the heat and how the sample exchange the heat with the surroundings, you know? So that amplitude and phase of temperature oscillation contain information about thermal diffusivity and conductivity of our sample. But since thermal conductivity and diffusivity of the sample is influenced by other sample properties, I mean, its internal structures, its optical properties, transport properties, on the basis of that, we can also extract from the measurements also information about these properties. So, so what are the properties of the temperature oscillation? About amplitude and phase, we also know. Another important parameters of that properties of that temperature oscillation is that they are highly attenuated in the medium. They propagate. It means both in the sample and in the fluid above that sample. So the attenuation factor equals its wave number, you know. We also determine how deep into the material the temperature oscillation go into it, inside, how deep the material they penetrate. So we define the thermal diffusion length that is strongly dependent on the modulation frequency of the excitation radiation. This is important information that we'll further use in our analysis. Yeah? So when we induced the temperature oscillation in the fluid above our samples, yeah, the optical properties of the fluid also changes, you know, especially we deal with the change in the refractive index of the medium, yeah. So that changes we further determined by another laser beam that is simply skimming the surface of the sample and probing the temperature oscillation induced in the fluid. And what happens to the laser beam, yeah, the probe beam, yeah, since it's just changed the direction from its initial propagation in both in the direction perpendicular to the sample surface and in the direction parallel to the sample surface, yeah, so it simply deflects in both this direction, so that's why the method is called beam deflection spectrometry. But to extract information from the measurements, of course, we need the support of theoretical model of that interaction. So we assume that our probe beam is a bundle of rays that propagates in the complex space. So when we induced in the fluid temperature oscillation, it changes the fluid refractive index and introduce the gradients of the refractive index in that fluid. So when now the bundle of rays propagates through that areas with temperature oscillation, each of that ray from that bundle simply deflects. What it means? It means that the coordinates of that ray changes from its initial propagation. So we need to find in our analysis the corrections to the ray trajectory. So when the ray is deflected, finally that changes the divergence of the rays, what finally leads to the change in the amplitude of the electric field in the probe beam, what causes its intensity change. Yeah? So this is one of the effects that we have with that we deal with when we are talking about the interaction of probe beam with the temperature oscillation. What is the other one? Yeah, since the refractive index of the fluid is changed, it also changed the optical path of our rays. Yeah, so we deal with the phase change, what also leads to the intensity change of the probe beam. But we also must be careful that the optical path of the ray can be changed because of two reasons. One of them is because of the change of the refractive index, but the other is the result of the change in the beam trajectory. So the beam is deflected, what also changed the optical path and finally the phase. So the phasal component of the signal also consists of two parts, one resulting from deflection and the other one resulting from change in the gas refractive index. Yeah, so having the changed intensity of the probe beam, we want to measure these changes. So in our analysis, we need to use the the position sensitive detector, from which we get two types of signal. One results from the difference in illumination upper and lower photodiode halves. So we call it the normal component of the signal. Mathematically, it is expressed like that. And the other one results from the difference in illumination between left and right of the photodiode half. And we call it the tangential component of the photodeflection signal. So finally, the measured signal consists of two components. But of course, the expression that we used are very complicated. So we usually make a lot of efforts to simplify the theoretical model as much as possible to make the analysis easier and faster. Yeah. So we would like to know if it's possible to simplify our 2D theoretical model to 1D. So we did the analysis for a chosen sample with non-thermal properties. The chosen sample was the aluminum sample. That the thermal conductivity and diffusivity are very, very, very well known. So we measured the signal as a function of modulation frequency, but for different ratios of the excitation and probe beam radius. Yeah. So we got the values of thermal conductivities and diffusivities in case of using 1D model, 2D model for different ratios of excitation and probe beam radiation. And what we can see, if we now compare the results for 1D model between themselves, we see that a significant differences at 0.05 significant level occurs if the probe beam ratio is smaller than 4. Yeah? So we obtained very, very different results. Such differences do not occur in case 2D model. Yeah. What is more, if we now compare the results obtained for 2D model and 1D model, we can say that if the probe beam radius is comparable to the excitation probe beam radius, the differences between obtained properties reaches of about 30%. Yeah. If the ratio is of around 3, they decreased up to 20%. But what is important, that if the ratio is higher than 6, there are no significant differences between the values obtained for 1D and 2D model. Yeah, and what is more, the differences are at the level of standard deviation received for the single determination. So what can we conclude? Yeah, that we can simplify our theoretical description, just making the probe beam radius at least 6 times smaller than the excitation one. Yeah. Yeah, so this is a kind of achievement, but we can analyze our signal further in even more details, so we can see how it behaves as a function of modulation frequency of the excitation radiation. Here we have the amplitude and phase of the signal for different radiuses of the probe beam. So what we see in general, we see that the signal decreases very strongly with the increases in the value of modulation frequency. Why it is like that? This is the result of strong attenuation, that with the increase of modulation frequency, the attenuation of temperature oscillation strongly increases, thus the signal decreases. But with the increase of modulation frequency, also the temperature gradients increases. What for white probe beams, the beams with high radius, the deflectional component, the component that results from the beam deflection, yeah, increases. So it may result in the increase of the total measured signal. Yeah. To see if it's really like that, let's see the total signal and both components. That one that is caused by deflection, and that one that is caused by the phase change. Yeah. So what we see that for relatively low modulation frequency, what it means low, it means that the radius of the probe beam is much more smaller than the length of thermal wave in the medium in which the probe beam propagates. So if the radius of the probe beam is relatively small and the frequency is relatively low, the components that dominates in the total signal is the phasal one. But if the radius of the probe beam is comparable with the length of thermal waves in the medium the beam propagates. The component that dominates in the total signal is the deflectional one. So just setting properly the experimental condition, we may arrange the experiment in such a way that we need to take in our analysis only one of the components of the signal. So how does the typical experimental setup looks like? So our sample that is analyzed is placed on the stage that enables the movement in the 3 directions. The pump beam is directed perpendicularly to its surface. It's shaped by a set of lens. Yeah, and modulated, in the simpler case, if our laser has such a possibility, we can modulate it by the use of signal generator, but we can also use electro-optic modulator, acousto-optic modulator, or if we want to perform the measurements at lower frequencies, it can be a simple chopper. So that excitation radiation induce temperature oscillation in the sample in the fluid over the sample, that in turn I detected by a laser beam from probeam laser that is also shaped by a system of lens. Yeah. Then detection is performed by quadrant photodiodes equipped with interference filter that let through only the probe beam reached the detector, yeah, and the signal is collected by the use of locking amplifier. The locking amplifier has the advantages that it measures the signal of a chosen frequency, so it measures only the signal that has the same frequency as the modulation frequency of excitation radiation. Due to that, you are able to measure low signal in the presence of high noises. Yeah, so this is the big advantages of the technique. Yeah, so the beam deflection spectrometry found application in many fields of modern science and industry. And the very basic application is the determination of through-plane and in-plane thermal properties. So such an analysis was done for a graphene sample that consists of a few graphene layers. Yeah. Such samples are very often used as heat conductors or heat energy storage systems, so the thermal properties play an important role in this type of application. So what we measured the amplitude and phase of the tangential component of our signal as a function of the distance between the axis of excitation radiation and probe beam. Yeah. So such configuration of the method we call a surface scan method, because by analyzing this type of the signal, we can get information about in-plane thermal properties. To get the values of through-plane thermal properties, we must use so-called frequency scan method. So we collect the signal as a function of modulation frequency of excitation radiation. This is what I emphasized at the very beginning, that changing the modulation frequency, we can change the depth from which we collect the signal for very subsurface layer to the bulk material. So our sample, the sample we analyzed, were loaded with different pressure because we wanted to see how the thermal properties, the in-plane and through-plane thermal properties, changes after such loadings. So what we received, the character of changes depends on the direction we are analyzing. So in case of through plane properties, yeah, the thermal conductivity increases with the increase in thermal diffusivity. Whereas in case of in-plane thermal properties, the thermal conductivity decreases when the thermal diffusivity increases. Why it is like that? Yeah, generally it's like that. That when we press the sample, the single platelets are breaking, rolling, unfolding. So in such a way, we introduce in the material more internal interfaces. Yeah, so in turn increases its thermal resistance. So the more pressure we apply to the sample, so they are more breaking and more rolling. So the thermal properties generally decreases, but the pressure is applied in the direction perpendicular to the sample surface, so the changes in plane and through planes are different, and the heat also propagates differently in both these directions, what results in different behavior of the thermal properties. So it was the very basic application of the beam deflection spectrometry. It has also more sophisticated ones. One of them is determination of optical and transport properties of semiconductor materials. Yeah, in such a case, when the excitation radiation is absorbed, then the absorbed radiation is released back in a form of heat. We need to take into account that we produce within the sample such internal heat sources, yeah, that results from the bulk recombination, surface recombination, and intraband, so-called intraband thermalization. Yeah, so such analysis was performed for a photocatalytic material, titanium dioxide, that is very widely used. Why it is widely used? Because it's relatively cheap and inert to environment. Yeah. So we wanted to determine its optical and transport properties to be able to foresee its possible application in water purification. For water purification purposes, yeah. So how it works, yeah, when we illuminate our titanium dioxide, just electron for valence band are transferred to the conductive bands, yeah. The holes that are left in valence band react with water molecules, and they produce so-called hydroxyl radicals that react with the contaminants in the water, with the organic compounds, and cause its degradation. On the other side, yeah, the electrons in conductive band react with the oxygen that must be all the time added to the water, and produce oxygen radicals that also reacts with the organic compounds. So finally, both these radicals degrade our pollutant, forming mineral end products. So titanium dioxide is widely used, but it has also very, very serious disadvantages, that its activation occurs mainly under UV irradiation. UV irradiation is only 5% of solar light spectrum, what makes the pure titanium dioxide photocatalyst very low efficient. So a lot of efforts are made to increase that efficiency. Yeah, how to increase the efficiency? They want to reduce the energy band gap and increase the electron hole recombination rates. Yeah, so the titanium dioxide is doped by the use of different molecules. The surface sensitization is performed. And what we did in our analysis, we modified titanium dioxide using copper or zirconium molecules. Yeah. So we performed the standard measurements as the amplitude and phase of the signal as a function of modulation frequency. We use our theoretical model and fitted it to the experimental data to extract the information about the energy bandgap and carrier lifetime of such modified material. What I need to mention here, yeah, that titanium dioxide as a semiconductor has both direct and indirect bandgap. But in beam deflection experiments, the signal is produced as a result of non-radiative excitation processes. So it means that we are unable to determine the values of direct bandgap energy because it corresponds only to radiative transition. So do not influence on the measured signal. Yeah. So if you would like to extract information about the bandgap using that technique, we must be aware of the fact that only indirect one may be determined. So what we received, yeah, regarding the bandgap, okay, generally after modification, its value decrease up to 13%, but it is strongly influenced or determined by the type of amount of particles it was incorporated into the structure. Regarding the carrier lifetimes, we can say that it also decreased. Why it decreased? Because performing the modification, we introduced additional defects within the volume of the materials that further works as recombination centers in the bandgap. But what is, I think, worth to mention that the uncertainty of determination by the use of this technique were at the level of 3%, what I think indicates that the precision is rather high. Another, I think, interesting application of the beam deflection spectrometry is the porosity evaluation of anti-corrosion coatings. You know, anti-corrosion coatings, it has a role of a barrier between the material that would like to protect and its environment, you know. So it means it should minimize any water penetration from the environment to the protected materials, yeah. The sample that we analyzed, they were hybrid organic, inorganic layers that were made of silicon materials, but we also examine how the porosity values changes when we change the radicals. So the radicals of our interest were from metal to dodecyl and laurel. So let's have a look. The sample of our interest was thick 4 micrometers, so it was necessary to perform the measurements and at high values of modulation frequency, just to get information or collect information only from our countings without the influence of the metal support on which the sample was deposited. So what we received, it's seen on that pictures where we have presented how the thermal conductivity and diffusivity changes with the change of determined porosity. So the porosity we find was relatively low values, you know, under 1%. So in case of anti-corrosion coatings, I think it's okay, yeah. But how the porosity changes if we increase the length of the alkyl chain of our acrylate monomer. So for shorter alkyl chain, as we have here, so it's methyl ethyl butyl. Yeah, if we analyze it statistically, we see that no significant differences in the values of porosity occur for the group of shorter alkyl chains. Yeah, if we compare the value of the pure silicon material, silicon-based material. But the situation changes when we increase the length of alkyl chain of our acrylate monomer. So for longer hexyl dodecyl, octyl dodecyl, the changes in the values of porosity increases. Why they increase? Because if we increase the length of the chain, we increases the number of radicals in that change. So the number of radicals increases the size and voids between the single molecules, what in turns increase the number of pores and finally reduct the anti-corrosion properties. So the conclusion from that can be that the best anti-corrosion properties show the samples with shorter alkyl chain of acrylate monomer. Yeah. Another environmental application of this technique of beam deflection spectrometry is its application for determination of iron species in the environmental sample. The sample that was under our interest was the polar sea ice. So for that purpose, we coupled our technique to the technique that is called the diffuse gradients in films. And that enables in situ sampling of label species, of label fraction of metal in different aquatic media or sediments, you know. So the probes looks like that. This is the probe that we use for determining the iron species in waters as lakes, seas, rivers, and that in sediments. In general, they consist of the same parts. So we have the probe upper and lower probe cover. Here we have filter and diffusive layer that has a role of protective layers, layers under which we deal with so-called binding resin that has the ability of selectively bind depending on the choice on the type of layer we pick up. So it has the ability of selectively binding the label fraction of metal inside it. So the idea is based of pre-concentration of this metal within that layer. So we got the time average information about such a concentration. So in our analysis, we took that layer and deposited on the glass support and left for drying before the analysis. So what we got, yeah, since in the first step we performed the colorimetric reaction of iron 2 with phenanthroline to form an orange colored complex with the maximum absorption of about 510 micrometers. Yeah? If you would like to differentiate between iron 2 and iron 3, we had to reduce iron 3 to iron 2 by the use of ascorbic acid, because only iron 2 reacts with phenanthrene and form the color complex. What is also important when we are talking about this application, that the concentration of iron in natural water is relatively low at the level of nanomolars. So we had to increase our sensitivity of the techniques. So we built a resonant cavity for probe beam, due to which the probe beam travels more time through the area of temperature oscillation. In such a way, we increased the measured signal and thus the sensitivity of the method. Yeah, and the method of detection is based on calibration curve. So in the first step, we had to build the calibration curve and determine the limit of detection. So for the optimized beam deflection spectrometer, it was of about 10 nanomolars for 5 days of deployment of our sample in the iron solution. We need to emphasize that LOD can be further decreased if we increase the deployment time. What it also is worth to say that the relative standard deviation of a single measurement was on the level of 6%, what indicates quite good reproducibility regarding the sample preparation, and indicates a homogeneous distribution of our analyte along the entire area of the analyzed gel. So when it was applied, as I mentioned, it was applied for determination of iron 2 and total iron distribution on the polar ice that was collected from the Davis station on the Arctic that belongs to the Australian Antarctic territory. So what we received, let's get a look on the other side. So generally, we put the gels directly on the polar sea ice. So we actually determined the distribution of the ice in the melted ice that was in contact with our sampler and the probe. Yeah. So we received that the concentration of iron is up to 250 nanomolars, if we are talking about iron 2, or up to 250 nanomolars, if we are talking about the total iron. So we can see from that measurements that beam deflection spectrometry provides a platform for the determination of 2D distribution of iron redox species also, yeah, when analyzing the sea ice. So the very last application about which I would like you to talk today is the depth profiling of multifunctional coatings used for medical application. Yeah, this is also related to what I already said. Yeah, so you would like to, such coatings are based of polysaccharide aerogels and are used as sophisticated drug delivery systems that are deposited on different type of implants of joints. So we would like to see how the diffuses of drugs occurs in such system by analyzing the change in the thermal properties of single layers. Yeah, so I already told it at the beginning that we can adjust the depth from which we would like to collect the information using these techniques by changing the modulation frequency of the excitation radiation. So we can scan our sample from bulk of it to sub-micrometer surface layers. Yeah. So in case of these samples, the measurements were performed at relatively high modulation frequency, up to 100 kilohertz. And what sample we analyzed? As I already said, they were multi-layered samples used as sophisticated drug delivery systems. Yeah. They were made of polysaccharide aerogels. Yeah, so we analyzed two-layered system that consists of hyaluronic acid and amoxicillin as that antibiotics, which diffusion into the below layer would like to examine. Yeah, another one was 2 layers of hyaluronic acid with amoxicillin layer between them. Yeah, and the last one of our interest consists also of 3 layers: hyaluronic acid, amoxicillin, and fucoidan. Yeah, so we would like to see how the amoxicillin diffuses inside these upper and lower layers by monitoring the changes in the thermal properties. Yeah, so what we have done in case of 2 layers, we built our theoretical model in such a way that we assume that between hyaluronic acid and amoxicillin exists diffusive layer. In case of the 3 layered samples, we have 2 diffusive layers: amoxicillin and hyaluronic acid, upper and lower part. So here and here is the diffusive layer. The same is when the upper layer is fucoidan. Yeah? We introduced in our theoretical model another diffusive layer, and all the diffusive layer were further divided into 6 sublayers. Yeah? So we performed multi-parameter fittings to determine the thickness of each sub-layer and determine their thermal properties. The criteria for finding the thickness of such a layer was 6 times standard deviation of the thermal diffusivity that was determined for only hyaluronic layer. Yeah, what is that one? So what we received, yeah, in case of 2-layer system, yeah, it's presented here. 3-layered system consisted of 2 layers of hyaluronic acid, and amoxicillin between them is presented here. And this is the 3-layered system with fucoidan as the top layer. So what we can see that the diffusion of, this is the thermal properties of amoxicillin, hyaluronic acid, and here fucoidan. And what can we see? That the diffusion of amoxicillin occurs in both hyaluronic acid and also in fucoidan layers. This is expressed or it's seen as the decrease in the thermal properties of both the layer of hyaluronic acid and fucoidan. So monitoring the thermal properties of each of the sublayers can be an indication of the rate of the diffusion process of our antibiotics. What can also indicate its efficiency of the whole materials for the purpose of drug delivery system. Yeah. So what can we say to conclude? Yeah, we can say that beam deflection technique has a big potential that is also non-destructive and highly sensitive, And what is more, it does not require complicated sample preparation procedure. It enables the measurements of temperature changes of the sample surface at the level of fraction of kelvins, what corresponds to the beam deflection of 10 to minus 9. Yeah? It can also be used in case of a wide range of samples that also absorbs very weakly, because it enables detection of the absorption losses at the level of 10 to minus 7. Due to which, or by the use of which, we can find the optical parameters of the sample as absorption coefficient or bandgap energy. We can determine, of course, the thermal properties of thermal conductivity and diffusivity, transport ones as Carrier lifetime, and structure as porosity, for example, what we saw in the presentation. And it's applicable to a wide range of samples that also inhibits significant scatterings, as powders are optically thick or are weakly absorbing and have no transmission. So thank you for your attention, and I'm happy to answer all your questions.